Okay, this is part one of the lecture on simple circuits. Okay, begin very simply by hooking up a battery to a wire. In order to illustrate that, I'm going to use, instead of a battery, I'm going to use this transformer here, and my wire is also going to have a light bulb that is inserted into this circuit. I'm just going to go ahead and turn it on like so, and then let some current flow. So let's begin to picture this circuit very simply in the following way. Okay, so right here, if you recall, is the symbol for the battery. This is the potential difference, the voltage V. And then I just have a wire like so, attached to a light bulb, which is over here, for example, on the right-hand side. Okay, recall that electrons flow through a conducting wire, and electrons always flow from low to high potential. So here's the low potential side of the battery. If you want to think of that as the negative side, that's fine. Here's the high potential side of the battery, like so. So then therefore the current then flows, the electrons then flow, like so, in this direction. However, electrons, of course, are negatively charged. It turns out that electrical engineers don't like negative signs. So because electrical engineers don't like negative signs, we actually ignore the negative sign associated with the electrons. Instead of having the electrons flow as they do from low to high potential, we always draw the situation instead backwards. We define what is meant by the conventional current. The conventional current is given the symbol capital I, and we say that it flows backwards of what actually happens. Once again, the electrons actually flow from low to high potential. However, by definition, we ignore the negative sign associated with the electrons, and instead we define the conventional current. The conventional current flows downhill. It flows from high to low potential instead. Like so. So the conventional current, by definition, flows backwards of what actually happens. This may sound initially confusing, but it actually makes things easy to deal with mathematically. That's why we bother to do it this way. Okay, now speaking of mathematics, there is a simple mathematical definition for the conventional current. It's equal to charge per time. So imagine standing, for example, at one point in the circuit, and you calculate, or count rather, the amount of charge that goes by per second. When you do, you are measuring the conventional current. Here's a nice analog that you can use. For example, imagine standing on the side of a river, and you simply count or calculate how much water flows by per second. You've measured a water current when doing so. This is the exact same thing, but instead of water, what we're talking about here is electrical charge. Okay, now we do have a new quantity here, so let's go ahead and check the units. Okay, charge is measured in terms of coulombs, and time is measured in terms of seconds. A coulomb per second is given its own name. It's referred to as an ampere, which is abbreviated very simply as capital A. Okay, now what about the speed of the current, if you will, as it flows through the circuit? Well, imagine what happens as an object falls from high to low potential. Ultimately, potential energy is transformed into kinetic energy, for example, as an object falls. And then therefore, if you drop an object in free fall, for example, it of course speeds up. Does the same thing happen with the conventional current as it flows through the circuit? That is, does the current speed up? The answer to that question is no. And the reason why is because as the actual electrons themselves are moving through the conducting wire, they interact with the atoms that make up the wire. This then ultimately causes some of the kinetic energy associated with those electrons to be lost as heat. This property is referred to as resistance. So as the current flows within the circuit, it does not speed up due to resistance. Resistance is the phrase that we use to describe what happens when the actual electrons themselves interact with some of the atoms that make up the metal. This interaction causes some of the energy to be lost as heat. So the electrons interact with the atoms that make up the conducting wire, the metal. Causing some of the energy to be lost as heat. This is why all electrical circuits heat up. Causing some of the energy to be lost as heat. Okay, here's a really nice simple analogy that you can use to picture what's actually happening to the electrons as they flow through the wire. By analogy, picture a pinball machine. Okay, so a pinball machine, of course, is tilted on its side like so. This right here is a region of high potential. It's at a greater height. This right here is a region of low potential. It's at a lesser height. Okay, now imagine taking a look at the pinball machine and then looking at it face down. So let's say that right here is the pinball machine itself like so. You're looking face down on it. Here's the high potential side, here's the low potential side, and then you have the pinballs. So right here are some pinballs. Okay, then if there was nothing in the way of the pinballs themselves, as they roll downhill, of course they would accelerate. However, in a pinball machine, there are things in the way, like the bumpers, for example, in pinball machines. Let me go ahead and put in some bumpers, like so. So as the pinballs then flow downhill, if you will, in the pinball machine, they don't get very far before they interact with some of the bumpers that make up the pinball machine, and then therefore that interaction causes some of the kinetic energy to be lost as heat. There's a general drift, if you will, of the pinballs down the hill like so, but as they flow downhill, they periodically interact with the bumpers of the pinball machine and then lose kinetic energy. That general flow downhill of the pinballs themselves, that by analogy is the same thing as the conventional current as electrical charge flows through a wire. The individual electrons themselves, when they move through the wire, are moving at speeds usually in the neighborhood of several tens of kilometers per second. But they don't get very far, however, before they hit an atom in the wire itself and then therefore lose some of the energy as heat. The overall drift itself of the conventional current through a wire is usually moving at a speed that is only about 0.5 millimeter per second. So we kind of have this idea in our heads that the current is just racing through electrical wires because we're somewhat fearful of electricity, of course, but that's actually not the case. The actual speed of the drift, if you will, of the conventional current is quite small. It's usually in the neighborhood of less than 1 millimeter per second. However, the motion of the individual electrons themselves is about 1 billion times that amount. 1 billion times that amount is several tens of kilometers per second, and that's then the individual speeds of the electrons themselves. However, as I said, they don't get very far. However, prior to actually hitting one of the bumpers in the pinball machine, if you will, and then causing some of the energy to be lost as heat. So just to kind of finish this description here, so as the pinballs flow downhill, they hit the bumpers and lose energy as heat as a result. Okay, so that's basically what's happening as the conventional current moves through a wire. Okay, let me go ahead and do some erasing here. There is a symbol that we use to describe resistance, this property that happens within the wire as the electrons flow through it. Okay, so now to indicate the resistance of the wire and or the light bulb, think of the light bulb itself as what is called a resistor. Basically, we combine the wire itself and the light bulb in my simple demonstration into a simple symbol, which we then draw in my original diagram. That symbol is drawn like so. A jagged line. This jagged line here is the resistor symbol. And it's referred to as capital R. So capital R, the resistance itself, is this property of what happens when the electrons themselves interact with the atoms that make up the metal and then ultimately lose heat. There is a very simple mathematical relationship between the following three quantities. The steepness of the hill, if you will, the voltage, the amount of current that flows, and the resistance in the wire. This simple relationship is usually shown as a graph, and most common metals that we use in wires, copper, aluminum, tungsten, and a few others, they basically obey this mathematical relationship. This mathematical relationship is a graph of how much current flows depending upon the voltage itself, the steepness of the hill. Like so. So in other words, the current itself is a function of the voltage V. So this is the independent variable, and the current, of course, depends upon the steepness of your hill. For most metals, the relationship between the two quantities on this graph is linear. Like so. Okay, now the slope of the line here has meaning. The slope of the line is equal to the inverse of the resistance R. So for example, if the resistance R is small, then the slope of the line would be large. What would that then mean is that a large amount of current would flow depending upon the potential difference V. However, if the resistance is really large, this then means that the slope here is small. So then therefore the amount of current that would flow would be small, once again depending upon the voltage V. So this new property called resistance here is basically the reciprocal of it, that is the slope of this graph. We can actually now write this graph mathematically in the following way. Current is equal to voltage divided by resistance. Think of this as the equation of a line. Y equals mx plus b, where the slope m is 1 over the resistance r. Usually we move the resistance r, by the way, to the other side of the expression, and we write the expression like so. B equals IR. This expression here is known as Ohm's law. Ohm's law is an empirical property that describes this graph here for most common metals. Most common metals are referred to as ohmic for this reason. Common ohmic metals are copper, aluminum, and tungsten. These are primarily the elements that we use in simple electrical wires. The reason why we do is essentially twofold. These types of metals are fairly common. They appear in various mineral ores in the earth, and we mine for it, and then hopefully we recycle as much as we can. But they also obey Ohm's law, this simple mathematical relationship. Okay, now we do have this new quantity called resistance here that is present within this expression. Let me describe the units of resistance. Okay, the units of resistance R is in terms of volts per ampere. A volt per ampere is referred to simply as an ohm. We give it the symbol capital Omega, and it's equal to volts per ampere, like so. Okay? Okay, now just briefly, here's a brief description of what happens in a non-ohmic situation. Okay, for a non-ohmic situation, a nice example of this would be what is called a superconductor. It's a term that you may have heard before. Some types of metals, when you cool them down to an extremely low temperature, this then dramatically lowers the resistance. So then therefore, for a certain amount of voltage, you don't need a lot of voltage to generate a lot of current because the resistance is really low. In superconducting metals, which usually occur at really low temperatures, the graph that you see on the top board is not linear. Instead, it's exponential. It looks like this. Like so. So for only a very small amount of voltage, you can then generate a lot of current. Sometimes if you cool certain metals down to extremely low temperatures. When you do, you are using what are referred to as superconductors, and that's a non-ohmic situation, okay? But primarily, of course, here at the introductory level, we just worry about ohmic situations because they're easy to describe. I can actually sort of show that here in this simple demonstration involving my light bulb. Once again, let me go ahead and turn it on like so. Okay, and now, right now, I've got a certain amount of voltage here that is present, and then based upon the resistance of the wires in the light bulb itself, that then determines how much conventional current flows. Okay, let me now just go ahead and increase the voltage. So if I increase the voltage, I don't change the resistance, but I do, of course, change the current. If you increase the voltage, you increase the current. Like so. If I decrease the voltage, I then decrease the current, like so, and the relationship between the two, current and voltage, as described on the top board, is linear, okay? All right, let me go ahead and turn this off. Okay, let me do some erasing here as well. Okay, a little bit about the energy transfer associated with a simple circuit in the context here of conventional current. Okay, first of all, let's concentrate here upon the battery, which has a potential difference V. Okay, now recall that potential difference V, the voltage is equal to the following. It's potential energy U per charge. That's equal to the voltage V. This then means that the potential energy of the battery is equal to the charge multiplied by the voltage. What I'm going to do is just take this expression here and divide it by time. When I do, you end up with energy per time, which is referred to, if you remember, as power. So ultimately, the amount of energy per time that is delivered by the battery as the conventional current flows is described in the following expression. So power, energy per time. It's equal to this guy here on the right-hand side of the expression, per time. Like so. And then notice right here, charge over time, we now have the conventional current I. We then rewrite the left-hand side of the expression here simply as the power P. P equals I times V. This quantity here is referred to as the power, the energy per second that is delivered by the battery. Okay, now in a simple circuit, such as what we've drawn here, what then happens to all of that energy? Well, ultimately it's lost as heat due to resistance in the wires. The resistor in this case is a combination of the light bulb and the wires that I'm using in my simple demonstration. Okay, how do we write that mathematically? Okay, this is referred to as the power loss. The power loss is the amount of energy per second that is lost as heat. Lost as heat in the resistor. Okay, let me go back up to my diagram above here to illustrate. Okay, so going back to my simple diagram here, once again, a little bit more in-depth meaning here with regards to the symbols. Okay, the resistance, symbol R, once again, is this jagged line right here. This is essentially representing the energy that is being lost as heat. However, notice that some of the other lines that have remained from the earlier portion of my description are still straight lines. Here and here, like so. We always draw straight lines in circuits to represent equipotential surfaces. So this then means that there is no potential difference between here and here because all of this is a straight line. There is no potential difference between here and here because all of this is a straight line. That may seem initially confusing because when you think about it, as the current flows through the circuit, it's always just flowing downhill in this manner, so then therefore it is always flowing across a potential difference. However, you have to remember that the entire wire is a resistor. It really doesn't make any sense to draw the jagged line all the way across the diagram like so to represent that resistor. Instead, we just draw it once, as I've done here off to the side, and we keep the symbol itself small. Therefore, any straight line that we draw, that then has to represent an equipotential surface. Very simply, what all that means is the following. The potential difference here of the battery V is the same thing as the potential difference from here to here, for example, as the conventional current flows downhill from high potential to low potential. So the potential difference V here is the same thing then, therefore, as the potential difference across the resistor. Therefore, that potential difference is equal to the current itself multiplied by the resistance R. Okay, let's use this then to describe the rate at which energy is lost as heat within the resistor itself. Here's how we do that. Okay, so now getting back to this calculation, P loss, we're going to combine together two things. First of all, from earlier, the power delivered by the battery is equal to I times V, and V is equal to I times R. Go ahead and first of all replace the V here with I times R from the diagram above. When you do, you end up with the following. You end up with I times R. This is equal to I squared times R. Once again, this refers to the rate of energy lost as heat within the resistor itself. Another way of writing the exact same expression is as follows. Instead of replacing the V here with I times R, instead replace the I with V over R. When you do, you end up with this expression here, V squared over R, like so. This V right here is the potential difference itself across the resistor, like so. Okay, now at this point, let me go ahead and do just a couple of examples from the lecture examples that I've posted for you here in the folder. Go ahead and take a moment to copy down the first of those examples. I'm going to erase the board here, and then I'll lead you through the solution. Okay, so I'm only going to lead you through the first of those examples here for part one of today's lecture. Let me go ahead and take you through that example right now. Okay, so we've got a 9-volt battery is connected to a light bulb with a resistance of 2 ohms. Like so. So here's our voltage V, that's equal to 9 volts. The conventional current I flows in this direction. Right here is a resistor with a resistance of 2 ohms, like so. Once again, V is equal to I times R. So then asks us, how many actual electrons leave the battery per minute? Well, the first thing that we have to calculate in order to answer that question is how much current I is actually flowing through the circuit. So let's go ahead and take V, the voltage, and divide it by the resistance to find the current I, like so. And when we do now, we have voltage divided by resistance, so 9 divided by 2 here, that ends up being 4.5. So this is 4.5 amps, like so. Okay, now the actual charge itself, of course, then that's referring to individual electrons. So now let's go ahead and write I is Q over T, where we're given that the time T is 1 minute, which is equal to 60 seconds. So imagine this. You stand on the side of a river and you basically time how long it, or rather you time 1 minute, and you then measure how much water flows past your location. We're going to do the same thing here, but in this case we're going to calculate the amount of charge Q. So the amount of charge Q is I times T. So it's going to be 4.5 amps and then multiplied by 60 seconds. So let me go ahead and multiply that out. Okay, and then we end up with 270 coulombs when we do. Okay, as we'll see, this is a lot of electrons because the charge of an individual electron is only 1.6 times 10 to the minus 19 coulombs. So then therefore, the last portion of the process is to do the following. The number of electrons is going to equal 270 coulombs, and then I'm going to divide by 1.6 times 10 to the minus 19 coulombs per electron. Like so. So notice that the coulombs here cancels, and then we'll end up with a number of electrons. As you're going to see, it's going to be quite large. So divided by 1.6 times 10 to the minus 19, and this comes out to be about 1.7 or so, I'll round it off a little bit, times 10 to the 21 electrons. So that's a lot of pinballs that are flowing through the pinball machine, if you will, per minute. So then therefore, that would be the amount of electrons that goes by your location if you were going to time how long it takes for this to occur over the course of a minute. Okay, let me go ahead and pause here for part one of today's lecture.